All right, today we're jumping right to the bleeding edge of engineering. We're talking about a world where we can build and break the most incredible objects you can imagine, all before they even exist. So let's get into it. So here's the big question, right? How do we design the truly impossible? I'm talking about things like hyper-efficient jet engines, or biomedical implants that are generations ahead of what we have now, or even buildings that can stand up to forces we can barely imagine. How do you even begin to test something that's never been built?
While the answer is surprisingly cool. You test it in a world made entirely of math. You build a digital twin, a perfect replica of it, and then you throw everything you've got at it inside a computer. This is the incredible world of simulation.
But to really get a handle on where all this is headed, we first need to talk about the foundational tool that makes it all tick. And that's something called finite element analysis, or you'll hear it called FEA. Okay, so picture any complex shape you can think of, a car chassis, a wind turbine blade, whatever. FEA software basically takes that object and digitally slices it up into millions of tiny, simple pieces. We call them finite elements. Then it solves the physics for each individual tiny piece and adds it all back together. And just like that, you can predict exactly how the entire object will react to things like stress or heat or vibration. It's the ultimate digital proving ground for engineers. And let me tell you, it's getting a massive upgrade.
So, where does this whole upgrade even start? Well, the first big frontier is in the materials themselves. I mean, think about it. A digital test is only as good as the digital material you're testing, right? And today, we are engineering materials that behave in ways that are just extraordinary.
You know, for the longest time, simulations were mostly about simple, predictable materials, like steel. You know how a steel beam is going to bend and break. But now we're dealing with so-called smart materials that have these complex, almost lifelike reactions to their environment. And that just demands a whole new level of simulation. And this slide gives you a great little taste of what we're talking about. You've got things like hyperelastic materials. Think of the giant bearings that let buildings sway in an earthquake without collapsing. Then there are piezoelectric materials. These are wild. They generate electricity when you squeeze them, which is perfect for creating smart sensors. We're also talking about shape memory polymers, materials you can program to unfold inside the human body for things like revolutionary medical implants. And we can even zoom way in and model the complex interactions inside something like a car tire to predict exactly how and when it'll fail. It's just incredible stuff. But here's the catch. Modeling these amazing materials with this insane level of detail, well, it creates a brand new challenge. It takes a colossal amount of computing power. And that necessity brings us to our next big frontier, the raw horsepower that makes all of this possible. We are talking about high-performance computing, or HPC, basically supercomputers. These are the machines that let us run simulations that are so incredibly detailed they would have sounded like science fiction just a decade ago. Take this, for example. Researchers can now simulate the entire complex, nonlinear behavior of a reinforced concrete building. That completely changes the game for designing safer, better infrastructure. And it's not just about brute force power. It's also about working smarter. Think of traditional FEA like building something with a fixed set of Lego bricks. That grid of bricks is what we call the mesh. But now, we have these new meshless methods, which are more like working with clay. They don't need that rigid, predefined grid. This makes them unbelievably flexible for modeling things with complex, shifting shapes, like, say, a fluid sloshing around in a tank, or for spotting damage in a structure in real time. It's a total game changer for certain kinds of problems. Okay, so let's recap. We have these super powerful computers, and we have these amazing material models. We can create what seems like a perfect digital twin of an object. But that leads to a pretty crucial question. Is a perfect computer model actually realistic? Because let's be honest, the real world isn't perfect. It's messy, it's random, it's unpredictable. And that's where the next big evolution in FEA comes into play. It doesn't fight uncertainty, it embraces it. It's called stochastic modeling. So instead of assuming every single part has the exact same material strength, which never happens in a real factory, it runs thousands of simulations where all those properties vary just a little bit. By doing that, engineers can build designs that are way more robust, designs that can actually handle all the imperfections of the real world. And this is where things start to feel really futuristic. We are now plugging artificial intelligence directly into this whole process. This table just lays out the difference perfectly.
Look at that goal row at the bottom. Traditional FEA is all about analyzing a design you've already made, but AI-enhanced FEA, it's about generating the optimal design for you. How? Well, look at the speed row. It creates these ultra-fast surrogate models that can explore millions of design possibilities in the time it would take a person to test just a handful. It's a monumental shift.
But even a perfectly optimized, super robust design isn't quite the full picture if it only accounts for one type of force. To really, truly capture reality, you have to see how all the different physics connect. And that brings us to our final frontier. It's a concept called multiphysics. And instead of running a bunch of separate simulations for different forces, multiphysics modeling couples them all together. So you start by simulating the mechanical stress on an object. Then you layer on the thermal effects, how it reacts to heat and cold. After that, you can couple in the electromagnetic fields. You keep layering it on until you see the complete, interacting picture of how a system truly behaves in the real world. And this lets us understand these incredibly complex interactions. Suddenly, we can see exactly how a huge steel bridge expands and contracts under the heat of the sun. Or we can model the powerful mechanical forces that are generated by the magnetic fields buzzing around high-voltage transmission lines. It's all about seeing the whole system, not just the isolated parts. So let's pull all of these threads together, because this isn't just a list of separate cool upgrades. It's a powerful feedback loop, right? More innovative materials demand more computational power. That power lets AI optimize designs against real-world uncertainty. And then that entire optimized system can be tested in a fully coupled multi-physics world where everything interacts. It all works together. As the source material puts it so well, this creates a cohesive vision. It's an engineering toolkit that doesn't just help us analyze our designs better, it fundamentally changes how we even arrive at them in the first place. This is a leap from just tweaking existing ideas to actually discovering completely new ones. It's just a profound shift, you know? We're moving from simply analyzing what is to intelligently discovering what could be. And it really makes you wonder, with digital proving grounds this powerful, what on earth are we going to build next?